We are given the problem that glacial acetic acid, the most concentrated acetic acid you can buy, has a concentration of 17.54. Calculate the concentration of acetic acid in a solution that is prepared by combining 15 milliliters of glacial acetic acid with enough water to make a 250 milliliter solution. So right off the bat, there are a couple of things we can initially determine from the problem. And this first thing that we can initially determine is that acetic acid is a weak acid. And this is a given considering that acetic acid is not part of the list of 6 strong acids. And this list of 6 strong acids looks something like this. So here we have our 6 strong acids, and every other acid is a weak acid. So the main difference between strong acids and bases and weak acids and bases are that strong acids and bases dissociate completely, while weak acids and bases dissociate partially. So let me put this into perspective using the strong acid HCl. So this is what the dissociation process of HCl looks like. So let's say I have 10 molecules of HCl and I add water. Now, because HCl is a strong acid, these molecules would dissociate completely into its respective ions, H plus and Cl. So again, these 10 molecules would go 10 over here to the H plus and 10 over here to the Cl minus, and HCl will be left with no HCl molecules. Now, on the other hand, a weak acid like acetic acid, which is most commonly known as vinegar, if I were to add water, the dissociation process would look different because weak acids only dissociate partially. So this process would look a little something like this. So we're going to take the acetic acid. We're going to add water. And this is going to dissociate into H plus ions and CH3COO minus ion. Now, during this dissociation process, the CH3COO minus ion is unstable, and it wants to recombine with H plus to form CH3COOH. Thus, an equilibrium is formed, meaning that this arrow turns into this. So as a result of this process is known as a reversible reaction, and it thus requires an equilibrium symbol. So again, if I were to take 10 molecules of acetic acid, these 10 molecules would never dissociate completely like these HCl molecules, and we'd always be left with some CH3COOH molecules. Now returning to the problem. So as we get back again, glacial acetic acid, the most concentrated acetic acid you can buy, has a concentration of 17.54. So when a concentrated solution is diluted, the moles before the dilution and the moles after the dilution remain the same. This means that the moles before the dilution are equal to the moles after the dilution. So in order to solve this problem, a proportion can be set up using the initial concentration given as well as the volumes given. And this would look a little something like this. So I'm going to set it up like this. Using this equation, or proportion rather, I can plug in my concentrations and solve. So our M1, which is our initial concentration, is 17.54. Our volume 1 equals 15 milliliters. Now, our M2 is our concentration that is prepared with the 250 milliliters of solution. So we don't have that one yet, so I'm just going to put a question mark. What we do have, however, is our final volume. So our V2 is 250 milliliters. Now, using this, I can just solve for the M2 value. And since we want to isolate our M2 value, we're going to have to divide by our V2 value. So when we set it up with our concentrations, it's going to look something like this. M2 equals our M1, so our initial concentration of 17.54, multiplied by our initial volume of 15 milliliters. And that's going to be divided by our final volume of 250 milliliters. Now to solve, since these are both values that are in milliliters, the 15 and the 250 milliliters, we can just cross out those units. And now we can use our calculator. So again, our 17.54 multiplied by our 15.0, all divided by our 250. And that's going to give us a value of 1.0524 or 1.05. Now that 1.05 is our M2 concentration, which is the concentration of acetic acid that is prepared when combining a 15 milliliter solution of glacial acetic acid with enough water to make a 250 milliliter solution. Okay, so now that we've finished with step 1, we get ready to move on to step 2. And step 2 says to calculate the pH of the glacial acetic acid in the solution you prepared in step 1. So in order to solve problem 2, we need to use the acid ionization constant Ka. And this acid ionization constant looks like this. And this acid ionization constant represents the fraction of the original acid that has been ionized in the solution, thus meaning that Ka is the value that is a reflection of the relative strength of the acid. So for example, the Ka of an acid would look something like this. So given the dissociation of, let's say, just some unknown weak acid, so now that we're given this dissociation of this unknown acid, we can use these values to show what our Ka would be. So like in other equilibrium constants, the products of the dissociation are placed on top of the reactants for the dissociation. So the Ka would be represented like this. Again, like I said, products over reactants, and that's going to be our Ka. So now that we understand what a Ka value is, we're going to calculate the Ka value for our acetic acid. So using our dissociation equation for our acetic acid, we're going to set it up just like we did for the example problem over here. So again, we're going to write the dissociation equation. So our Ka value for our acetic acid would look something like this. Ka equals again, products over reactants. Now this Ka value is a standard value that is given for acetic acid. So this value we can just pull up from a table for our Ka. So our Ka value for acetic acid is actually 1.8 times 10 to the negative fifth. Now given that we understand how to set up a Ka value and what an acid ionization constant is, we can use this Ka value given to identify the H plus concentration of acetic acid. Now what this H plus concentration is going to tell us is going to tell us the pH of the glacial acetic acid, because pH is equal to the negative log of the H plus concentration. So an ICE table essentially represents the initial concentration, the change in concentration, and an equilibrium concentration of a solution. So in order to set that up, it's going to look something like this. Again, we're going to be using our dissociation equation. And I'm going to write our ICE table, which is represented as ICE on the side. And again, when we're using this, just like in our equilibrium constants, our H2O, because it is a liquid, isn't going to be included in our ICE table. So we can go ahead and cross that out. That's something that I like to do to help me keep things straight and orderly in my table. Now, we're going to be using, for our initial concentration, is going to be our value, our M1 value. So our M1 value is 17.54. So we're just going to write that right here, 17.54. However, we don't know the initial concentrations of our H plus ions and our CH3COO minus ions. So we're going to write zero values in our I location on our table. What we do know is that this is our only value that we have, meaning so that when our value changes, it's going to be a negative because it's the only value that we can actually lose. Meanwhile, since these are both zeros, we can only gain when we change. So we're going to add x's. So for our equilibrium concentration, it's going to look something like this. 17.54 minus x. And these are just simply going to become x's. These x's are just used as a representation to show the changes. It's a lot easier when you can visualize the changing process in an ICE table in order to calculate the values. So again, we are given the Ka value for our acetic acid. So using this and our ICE table that we have established, we can set it up as Ka equals to 1.8 times 10 to the negative fifth. And that's going to equal our equilibrium values. So our equilibrium values for our H plus ions and our CH3COO minus ions, we can combine them to get an x squared value. And that's going to be all over our 17.54 minus x value. Now, because the Ka value is such a small number, it's raised to the negative fifth, it is a very small number, we can disregard this x at the bottom of our relationship that we established here. So now that we've gotten rid of that x, we can just solve for the x squared. So now that we have this equation established, we can multiply our 17.54 value by our Ka value to solve for x. So when we do that, we get a value of 3.16 times 10 to the negative fifth equals x squared. Okay, now that we have this value, we're almost done. We still do have to solve for x. So in order to do that, we're going to have to take the square root of our 3.16 times 10 to the negative fifth value. So when we do that, it's going to look something like this. And our x value comes out to 0.0178. So now that we've given this x value, what is this x value? This x value represents our H plus concentration. So like it's shown in the ICE table, we don't know our H plus concentration, nor do we know our CH3COO minus concentration. But these are a 1-to-1 ratio since there's no coefficients in the front of these dissociation equation. So we can assume that they are the same. And as I stated before, our pH value, what we're looking to calculate for our step 2, is equal to the negative log of our H plus concentration. So now that we know what our H plus concentration is, we can take the negative log value of it, and that'll give us our pH for our glacial acetic acid. So when we do that, our calculator gives us a value of 1.75, which again is our pH. So now that we've used the ice table to find our pH for our glacial acetic acid, we can use it to find our pH for our diluted solution that we created in step 1. So again, we can set up another ice table. So CH3, COOH, aqueous, plus H2O, liquid, gives us our H plus ions and our CH3COO minus ions. Again, before, like our other previous ice table, water's not included, and we can set up our ICE values. However, instead of using our initial value that we used in this ice table, the 17.54, we're going to be using the concentration that we calculated in step 1. So our M2 value is what we're going to be using for our initial concentration in this ice table. And what we calculated was 1.05 M. So we're going to put that right here in our I slot. And just like the previous ice table, we don't know the H plus concentration in the diluted solution, nor do we know the CH3COO minus concentration in this diluted solution. So we're going to use zeros again. What we do know, again, we know the change. This is our only value that we're given, so we have to lose some of it. And we aren't given these values, so these can only gain. Like before, 1.05 minus X is going to be our equilibrium concentration, and Rx is going to be our equilibrium concentrations for our H plus and CH3COO minus ions. Now, solving just like before, we're going to follow the same steps as we did to calculate the pH of our glacial acetic acid. So we're going to use that Ka again for our acetic acid, that 1.8 times 10 to the negative 5th. And we're going to set that up to our X square values all over this value, our equilibrium change for this acetic acid. Now again, because our Ka value is very small, we can disregard this X right here, and we can solve for the X squared. So again, we're going to do 1.8 times 10 to the negative 5th. We're going to multiply that by our I value, our 1.05, and we're going to get, from that multiplication, we're going to get 1.89 times 10 to the negative 5th. Now, just like we did before, we have to solve for the X squared value, and the only way to do that is to take the square root of our value that we've calculated here. So when we do that, our X value comes out to be 0.00434, and when you take the negative log of that to calculate for the pH, you get a pH of 2.36. So there we go. We have our pH for our glacial acetic acid and our pH for our diluted solution. Now moving on to problem number 3. An unknown acid is prepared by diluting enough water to make a 1-liter solution. This solution of unknown acid was found to have a pH of 2.74. Calculate the Ka of this mystery acid. To solve this problem, let's consider the example of the unknown acid I used earlier. Now, if I were to set up an ice table for this association equation, it would look something like this. Now again, we're using the same variables we used in the ice tables before: the initial concentration, the change in concentration, and the equilibrium concentration. So since this is an unknown example, we're just going to use some made up values. So we're going to use C as our concentration, and 0 like before, because we don't know these concentrations of the H+ ions and the A- ions. And again, because this is the only concentration we're given, we obviously have to lose this concentration, so it's going to subtract, and we're going to add to this concentration. So it would be C minus X for the equilibrium concentration, and it's going to be X's for the concentration of H+ and the A- ions at equilibrium. So given this ice table that we just set up and this Ka values that we established earlier, we can use these values to plug in for our Ka. So our Ka is going to look something like this. Our Ka is going to be equal to X times X all over C minus X. Again, we don't have these or unknown variables. We're just making up an example to help explain problem number 3. So now that we have this is best what it's going to look like when we're solving for problem number 3. We're going to be solving for both C and for X values. In the problem above, our C is going to be represented by the molarity, which is the moles of the solution all over the volume of the solution. So given in the problem, we are given that solution is made by adding 0.19 moles to 1 liter of solution. So in order to calculate molarity, we have to use this molarity equation. So it's going to look like this: 0.19 moles all over 1 liter of solution is going to equal 0.19 molarity. Now that we have our C value, we can calculate our X value. And like we did in our previous ice tables, our X value is the concentration of the H+ ions, or the hydronium ions. And now that we have both our C value and our X value, we can calculate for our Ka, which is, we're going to set it up looking similar to this. So as you write it out, our Ka is going to look like Ka equals 1.82 times 10 to the negative third, squared, of course, and that's going to be all over the C value, so 0.19, minus 1.82 times 10 to the negative third. So when we use our calculator, we get a Ka value of 1.76 times 10 to the negative fifth. Problem number 4 states that a buffered solution of acetic acid can be prepared by combining 100 milliliters of the solution from problem 1 with 1.65 grams of sodium acetate. Calculate the pH of this buffered solution, and it's okay to assume the volume of the solution does not change by adding the salt. So let's go into detail of what a buffer is. So a buffer is a solution containing appreciable amounts of a weak conjugate acid-base pair. So basically, to make a buffer, you need a weak acid plus a salt derived from that acid, or you need a weak base plus a salt derived from that weak base. And buffers, they resist a change in pH, or they help the solution resist a change in pH when small amounts of a strong acid or a strong base are added. So in this problem, the buffer is created by adding 1.6 grams of sodium acetate, which is the salt that is derived from the weak acid, acetic acid. And in order to solve for the pH, we need to do a couple more steps before we can just jump straight into the pH calculation. So in order to do this, we first need to start off by calculating the molar mass of acetate. So the molar mass of sodium acetate is 82.03 grams per mole. Now, using this molar mass of sodium acetate, we can calculate the moles of sodium acetate in the solution. And the moles is calculated by dividing mass over molar mass. So in the problem, the mass of our sodium acetate is 1.65 grams. And our molar mass of our sodium acetate is 82.03 grams per mole. Now, dividing this, you get 0.0201 moles. Now that we found the moles, we can calculate molarity. And molarity is calculated as moles over volume. So again, we use the moles that we just calculated, so 0.0201 moles. Okay, so now that we have our moles set up, we need to set up for our liters. So molarity is calculated by moles over volume, but the volume has to be in liters. And in our problem, we are given our volume in 100 milliliters. So we just need to convert that to liters, which is going to be approximately 0.100 liters. So when we solve for molarity, we get a value of 0.201 molarity. Now that we have our molarity, we can go back to our Ka. So our Ka value, as we stated before, is 1.8 times 10 to the negative fifth. So we are going to need this value. So now that we have our Ka, we're actually going to need to be using something called the pKa. And the pKa, just like the Ka, is used to measure the relative strength of an acid. So the pKa is a value that is found by taking the negative log of the Ka. So it looks something like this. And when we plug our numbers in, our pKa value should look something like this. Negative log of 1.8 times 10 to the negative fifth. And when we do this math, we get a number of 4.74. And now that we have our pKa value, we can use something called the Henderson-Hasselbalch equation. The Henderson-Hasselbalch equation looks something like this. Our pH is equal to the pKa plus the log of the salt over the acid. So according to the Henderson-Hasselbalch equation, when the concentrations of the acid and the conjugate base are the same, so when the acid is approximately 50% dissociated, the pH equals the pKa of the solution. So this is the way that we're going to solve for question number 4. So in order to do so, we're just going to plug in our values that we calculated a few moments ago right here. So again, our pH is equal to our pKa plus our log of our salt. Now our salt is that sodium acetate. And our acid is acetic acid. So our pH is going to look like this. pH is going to be equal to 4.74, which is our calculated pKa, plus the log of the concentration of our sodium acetate. So the concentration of our sodium acetate, as we calculated before, is 0.201 molarity. So that's going to be our top number. Back when we did number 1, we calculated the concentration of our diluted solution of acetic acid as 1.05. So we're going to use that value here for our concentration, since, as it states in the problem, we're adding it to the solution from problem number 1. Now, when we solve, our pH value comes out to be 4.02. Using this pH value, we can then go on to solve for problem number 5. Now that we have our pH, we can go on to calculate our answer to question number 5, which asks us to calculate the pH of your buffered solution from problem number 4 when 1.0 milliliters of 6M HCl is added. So just like problem number 4, we're going to have to start off by calculating the moles of HCl that is in the solution. So the problem gives us the molarity of our HCl as 6M. So I'm going to write that as 6 moles per liter, which just gives us a better visualization of what molarity is. And it also gives us our volume in milliliters. and it gives us that as 1.0 milliliters. So I'm going to have to convert that to liters, which I have right here as 0.001 liter. And when you multiply that to get your moles, you get 0.006 moles. So as I showed before, HCl is a strong acid, meaning that it dissociates completely into its ions. So this dissociation equation for our HCl is going to look like this. Now, because we're given the 0.006 moles of HCl, we know that our hydronium, or H plus concentration, is also going to be 0.006 moles, as well as our Cl concentration. Now, continuing on, we already have our moles of sodium acetate like we did to solve for problem number 4. We need to now calculate the moles of acetic acid that we have in our current solution. And we can go again by using our values from problem number 1 to solve this. So again, molarity is calculated by moles over volume in liters. So in order to find the number of moles, we can use moles equals molarity divided by volume. So again, like we calculated in problem number 1, our molarity is 1.05 for our acetic acid. And in order to find the moles, we have to divide it by our liters of our solution. Our solution in problem number 4 was made with 100 milliliters, meaning that in order to find the molarity, to find the number of moles, we need to convert this milliliters to liters. So this 100 milliliters is going to turn into 0.100 liters. So when we multiply this value, we get 0.1052 moles. So now we have both of the moles of our HCl as well as the moles of our acetic acid. So using these values, we can again set up another ice table to find our pH. So as we set up our ice table, it's going to look something like this. So now we're starting off with our conjugate base of acetic acid, which is CH3COO-. So as we set up an ice table, using our initial concentration, our change in our concentration, and our equilibrium concentration, we're going to use the values we calculated above as well as the values we calculated in problem number 4. So in problem number 4, the moles of our conjugate base, our CH3COO, was calculated to 0.0201. So that is going to be our initial I for our CH3COO. Now we do know our hydronium, or our H plus concentration, as we just calculated above, is 0.006 moles. And our CH3COO concentration is, as again, we just calculated above, 0.1052. Now, since we're adding HCl to this solution in problem number 5, our change is going to be determined by our value of our H plus ions. So, since we start off initially with our 0.006 moles of our H plus ions, it's only makes sense that our values are going to change by 0.006. So our initial concentration for our CH3COO- is going to lose 0.006, as well as our H plus ions. And our CH3COOH is going to gain 0.006. Now, as you subtract and add these values, our equilibrium concentration for our CH3COO is going to come out as 0.0141. These values cancel each other out, and this is going to be 0.0992. So now that we have these values, we're going to use the Henderson-Hasselbalch equation again, as well as the values used in the Henderson-Hasselbalch equation from part 4. So just to reiterate, our Henderson-Hasselbalch equation looks like this. pH equals the pKa plus the log of the salt over the acid. Now plugging in the values, our pH is going to equal our pKa, which as we calculated before, as 4.74, plus the log of our salt over our acid. Now this is our salt, and this is our acid. So it will look like 0.014 over 0.0992. Now, as we solve for our pH and we multiply, our values come out to 3.89, which is our pH for problem number 5.